Welcome back. Now we move to section 5.2 about the inverse function theorem, and I'm going to split the section into 3 videos in order not to make very lengthy videos. So we are going to elaborate in full generality some of the ideas that we discussed in the one-dimensional case in the introduction. So if we have two isomorphic norm spaces E and F, an open subset V of E and an open subset W of F, and a bijection F from V to W that satisfies the following conditions. F is differentiable at A, at the point A in V, and the inverse of F, that I call G, is continuous at the point B equal F of A, then the following conditions are equivalent. The inverse is differentiable at B if and only if the derivative of A is an isomorphism. And in this case, the derivative of the inverse is the inverse of the derivative. Okay, so simple and so easy. So 1 implies 2 and 2 implies 1. 1 implies 2 is just the idea that we discussed in the introduction. By definition, G is the inverse of F. So we can write G of F is the identity of E. So when I differentiate it with the chain rule, I get G prime of F of A, which is G prime of B, composed with F prime of A, is the derivative of the identity at A. But the derivative of a linear bounded map at any point is the linear bounded map itself. So this means that, so it means that G prime is the left inverse of F prime. And now if I consider the other identity, F of G equals the identity of F, and we differentiate it with respect to B, I get that G prime is also a right inverse of F prime. So this means that F prime of A is bijective and its inverse is just G prime of B. And by definition, F prime of A and G prime of B are bounded. Therefore, F prime of A both actually are isomorphisms. So this is just 1 implies 2. Now, 2 implies 1. 2 implies 1. Okay, so we denote the argument of F by X and the argument of G by Y. So first we start by writing the differentiability condition of F at A. So we can write Y minus B minus the derivative in the direction of the difference, which is just F of X minus F of A minus. This is a remainder, and this remainder is a small o of the difference as X tends to A. Okay, this is just the condition. And now I know that F prime of A is an isomorphism. So when I multiply by the inverse of F prime of A, both sides, I get F prime of A inverse times this, minus F prime of A times F inverse times F prime of A, which is the identity. So I get X minus A here. And here I get F prime of A minus 1 times the remainder. So I can write this as well. So I can write X minus A is equal to this term minus this remainder. So X minus A, which is just G of Y minus G of B, is this term, F prime of A minus 1 at the direction Y minus B, minus this, so the inverse times the remainder. Okay? And we see here that the linear part in Y is this term. Okay? So if you prove that this is a small o of Y minus B, we are done. Because we are going to prove that G is differentiable at B. And necessarily then, the derivative of B is this guy. Okay, so this is what we are going to prove. So we're going to prove that for every positive epsilon number, for every positive number epsilon, we can find a positive number beta such that this remainder is less than epsilon times Y minus B, a norm, whenever the norm is less than beta. Of course, it's enough to prove this for epsilon smaller than a fixed constant. So here I'm going to take this constant, the norm of the inverse of the derivative. Okay, because if I prove this for epsilon less than this constant, then it's true for every epsilon positive. Because if epsilon is bigger, then I take another epsilon prime less than this constant, and therefore, okay, so this is, so it's enough. This is enough to prove it for epsilon small enough, actually. I need this restriction a little bit. So now let us write the condition that r of x is small o of x minus a as x tends to a. This means that, in particular, r of x is less than any positive constant times x minus a, provided x minus a norm is less than alpha. Okay, and instead of epsilon, I take epsilon over twice this times the square of the inverse, the norm of the inverse of the derivative. Okay, you'll see why. Okay, therefore, by the fundamental operator norm, the norm of this guy is less than the norm of the operator from a minus 1 times the norm of r of x. And so but when I multiply this inequality by f prime of a minus 1, I get epsilon over 2x minus a over the norm. So just cancel by 1 squared here. And since epsilon is less than this norm, the ratio is less than 1, and therefore this quantity is less than 1/2 times the norm of x minus a. This is the first condition. And now, if I go back to equation 3, okay, I can write f prime minus 1, f prime a minus 1, y minus b equal to x minus a plus this remainder. Okay, and by the second form of the triangle inequality, this norm is bigger or equal than the norm of x minus a minus the norm of the remainder. Okay, you can just write minus minus if you like in this way, but the norm of minus this guy is the norm of this guy. Okay, and now I use equation 4, inequality 4. The norm of this remainder is less than 1/2 norm of x minus. So minus this guy is bigger or equal than minus half x minus a. So this right-hand side here is bigger than norm of x minus a minus 1/2 the norm of x minus a, which is 1/2 norm of x minus a. Therefore, when I multiply by 2, I get that the norm of x minus a is less than twice the norm of f prime a minus 1 y minus b, which is, by the operator norm inequality, is less than twice the norm of the operator times the norm of y minus b, provided, of course, x minus a is less than alpha. Okay, now continuity of g at b implies that x minus a is less or equal than alpha if y minus b in norm is less than beta. Okay, now this is actually a subtle point, because why not just take beta equal alpha over this constant, 2 norm of f prime a minus 1. Okay, this would work, but this inequality is true, equality 5, is true if provided x minus a is less or equal than alpha. So, but how do I know that x minus a is less than alpha in norm if y minus b is less or equal than beta? We don't know that. This is the continuity actually of G. Okay, so if in terms of so intuitively, what does this inequality means? It means that if y minus b is small, then x minus a is small. Okay, and this expresses just the continuity of G at B actually. This is just G of B. Okay. So if I use estimates 4 and 5, what do we get? So according to estimate 4, I use just this one. The remainder is less than epsilon over twice this constant times the norm of x minus a times the norm of x minus a. Okay, so and now I use inequality 5. The norm of x minus a is less or equal than twice the norm, this constant times y minus b, and I get a cancellation, and I just get epsilon norm of y minus b. Okay, and this precisely means that the remainder is a small o of y minus b, and therefore, if we go back to this equation, we see that the linear part is that, and the remainder is a small o of y minus b, and this proves that g is differentiable at b, and its inverse is necessarily the inverse of f prime of a. Okay. Actually, I stated this lemma with minimal conditions. Okay, so I didn't use completeness. I didn't need continuity on the whole domain, just needed continuity at one point. And as a challenging exercise, what if you remove this assumption? Okay, if G is not continuous at B, we cannot conclude that G is differentiable at B. Okay, and I use continuity of G in a subtle way, actually, here in this identity. Okay, this is G of B. Okay, now I'm going to end this video by stating the inverse function theorem, or the local inversion theorem, version 1, and I will prove it in the next video. So here's the result. We have two isomorphic Banach spaces E and F, and a differentiable map, differentiable everywhere, from an open subset on an open subset U of E into F, such that the derivative of f is continuous at A, and the derivative at A is an isomorphism. Now, always start with checking that the spaces are isomorphic, because if they are not isomorphic, then the whole discussion is empty. Then there exists a neighborhood V included in U of A, and an open neighborhood W of B, such that f is a homomorphism between V and W, and the inverse is differentiable at the point B, and as you know, the derivative of the inverse is the inverse of the derivative. Okay. Now, unlike the lemma 5.1, we did not assume that f is a bijection or that f minus 1 is continuous, because this is the conclusion. In lemma 5.1, I assumed that f is a bijection, okay, and that f minus 1 is continuous at the point. But here, this is what I want to get. Okay? So it would be redundant of assuming it. Okay. So let me just mention the plan of this. The proof is a little bit lengthy, but here's the strategy. So we divide the proof into 4 steps. First, we write the equation y equal f of x that I want to solve as a fixed point problem. Then I show that this fixed point problem has a unique solution provided y is in some closed neighborhood w bar of B. So this defines a map G from w bar into E that to each y in this closed neighborhood, it's a closed ball actually, associates the unique solution of this equation. Okay. Third step, we show that G is Lipschitz continuous, and we conclude that when we restrict f to a smaller neighborhood, we find a neighborhood V of A such that f is a bijection between V and W, and then the inverse must necessarily be G. Okay, and we conclude with lemma 5.1. Okay, so this is the plan that I'm going to elaborate in the next video. So thank you for your attention, and see you next time.